Welcome to the final design video for the Group 2 of the OGO Automotive Energy Challenge. As we all know, internal combustion engine cars produce a lot of CO2 emission. And electrical vehicles, drive way more efficient. Now, it is a big challenge for electric cars to be implemented in the normal world, in the automotive world, because they don't run for as long distances as internal combustion engine cars do. And also it takes a lot of time to charge them, etc., etc. So also the lithium-ion batteries in most cars, most electric cars, take a lot of CO2 to produce. So these are big challenges that we face in this world. Now we need to maximize driving distances so we can drive further with the same energy as we used to. And in order to do this, we need to make the cars as efficient as possible. Now, the OGO Automotive Challenge is hosted by the Electromechanics and Power Electronics research group, and they have given us a 1 to 5 scale Audi A4 electric car, which we need to drive around a track at the Metaforum building on the TUE. And the goal is to drive 5 laps around this track as efficiently as possible, just so using as few watts out of our battery as possible. Now, to research the car as efficiently as possible and to get the best results out of our data, we have divided the challenge into 4 subjects with 4 subgroups. Now, these subgroups are the tank-to-wheel analysis. We have people working on a driving strategy. We have a sophisticated speed measurement system, and we have a highway-style toll payment system. Also, in preparation for the data for things like the tank-to-wheel analysis, we have 3 test plans, which we'll talk about later. Now, our motivation as a group for this project is we need to reduce the global carbon footprint, of course. Also, it gives us a lot of insight in how electronics and mechanics work together in vehicles and other things. And also, we hope to provide useful data for the EPE vehicle department. And that was the introduction to this project.
So, in order to get the car to drive as efficient as possible, a few tests had to be done in order to find the optimal speed and efficiency of the car. So, 3 tests have been done: a rolling resistance test, a dynamometer test, and a wind tunnel test. Let's start off with the rolling resistance test. This was done in front of the Metaforum in the Markthal. The car would be given a push, so it would then decelerate, and this deceleration could be calculated using the difference in speed over the difference in time. This would then be uploaded to a Arduino, and you could download it from the Arduino onto the computer, and the deceleration could be found. Then we would call the deceleration of the car, that would be the total force on the car, and this will be equal to the mass times the deceleration. As soon as the car was not pushed anymore, the push force of the person pushing the car will be equal to 0. So there will be 2 forces left which would decelerate the car. One of them will be the rolling resistance, and the other one will be the air resistance. Well, the air resistance will be determined in another test, so that will be constant for a certain velocity, and then using the formula C times M times G, we could then calculate the coefficients, the rolling coefficients of the car, and this could be done with and without the electromotor attached. So these were our values for the rolling resistance without the electromotor attached, so it will be 0.033818. This was determined by using all the data of the test, and these will be put in Excel all these Excel sheets, we made a few graphs, and these graphs would show the deceleration, and with all the forces that we calculated in the other tests, we could then calculate the rolling coefficient without the electromotor, and we also did it with the electromotor. So that would be a little higher, but still be relatively low. It will be 0.09161.
Now the second test we performed on our model car to acquire more data is the dynamometer test. In the dynamometer test we actually performed 3 different tests, which one test we already got the results from the TUE itself. Now the first test is with the motor cogwheel in the car removed. This is in order to calculate what the efficiency is of the roller bench and what the resistance is of the rolling bench. So then we know if we have our results from our rolling bench, we have to take a small percentage of that force, we have to take it off, so we know what power the wheels are exerting on the roller. The second test is with the motor attached. So we have created a MATLAB road load profile, which we let it run on the dynamometer, and this one tests all the efficiency. It measures the how much watt comes out of the battery, so the power. It measures the voltage. It measures current, and it is all different speeds, forces, and at different distances. So we acquire as much information as possible about our model vehicle in a short amount of time. And as a third test, we have a standing still test. This means no power of the battery is going to the electromotor, and all the power that is consumed is by the auxiliaries, like the lights on the side of the car and the Arduino motherboard that's in the car. And that's also very important to know how much these consume.
Wind tunnel test was performed at the wind tunnel here at the TUE. We had 4 different configurations of the car to see what the effect was of adding things or not adding things to the car. We had a bottom plate with a front splitter and tape. We had a bottom plate with a front splitter, only front splitter, and nothing at all. We measured at 4 different wind speeds, which is 2, 4, 8, and 12 meters per second. And eventually, with all that data, we could calculate the coefficient of drag. We used the frontal area, which we calculated was between 0.064 and 0.067 square meters. We calculated with Clonk, which is a program from which you can use to measure areas from a picture. Eventually, we found out that the coefficient of drag was between 0.655 and 0.758, and the lowest was 0.655, and that's with an area of 0.067. That's what we used in our calculations. All this data was collected and eventually used in the tank-to-wheel analysis. There are 3 forces which we have to take into account, which is the aerodynamic drag, the rolling resistance, and the force it takes to accelerate the car. With the dyno test, we also got the optimal speed, and we made a model which calculates how much energy has to be used to complete 1 lap of the track. The optimal speed was measured using the efficiency. We took the power to the wheels and we divided it by the power to the battery. And we found out that the efficiency was between 0.065 and 0.25. We put this in the model at each speed with each efficiency, and we had the model calculate the total joule outcome, and eventually we saw it was most efficient around 24 kilometers per hour, and we eventually choose the optimal speed of 12 kilometers per hour, because then we don't have to brake as much, and it's still really efficient. The difference between 24 kilometers per hour and 12 kilometers per hour is not that much, but it will make a big difference because we don't have to accelerate and brake that much. Because when you accelerate, the motor tends to put all its power to accelerating, and it's really inefficient. The model we used, these are the formulas we used, is the aerodynamic drag, the rolling resistance, and the acceleration force needed put together. Those are the forces which the power of the motor needs to overcome. And we divide it by the efficiency, and that's the total force which needs to be put out by the motor or come out of the battery. Then we calculate the power by multiplying the force with the speed, and we calculate the energy by multiplying the power with the time. And eventually we found out for one lap at 12 kilometers per hour, it takes 44 kilowatts and 1879 kilojoules to complete one lap.
So, using this tank-to-wheel analysis, we can determine a driving strategy. There are three main points that we used so that the car would use as less power as possible. So first of all, we want to avoid aggressive driving. So what do we mean by this? That this means that we don't want to accelerate really quick. As you can see in this graph, it was taken from a dynamometer test. When accelerating, you can see that the power output would be too large and too big, and while driving at constant speed would be using not a lot of power. And we want to avoid the braking as much, because that's what we also consider as aggressive driving. As when you need to brake a lot, we also need to accelerate again, which uses again a lot of power, as seen in the graph. One more thing we would like to do during the test day is, instead of braking in the corners, we'd like to let the car coast down, as this would again avoid excessive deaccelerating and then again excessive accelerating. And the car will actually coast down by itself due to these two formulas, the FR and the rolling resistance. And due to the fact we won't give any power to work against these air resistance and rolling resistance. So our basic 2 points were: try to drive at a constant speed, so don't really brake in the corners, as that would result in having us to accelerate again, and not too high speed, as that would also, as seen here, were the lower points, that when a higher speed it would consume more power than driving at a lower speed. And next, what I just told about cornering, why we actually don't want to drive at 24 kilometers per hour, which we would consider at the most energy efficient speed. That would be that is because if we drive at this speed, then we wouldn't remain on the track. We will just slip out, or even worse, we will just roll over. So that's why we chose for an optimal speed of 12 kilometers per hour, because due to the fact that these formulas, it means that we won't slip when we fill in 24, or when we calculate the optimal speed to drive through this corner. We see that the 24 kilometers per hour is way too big, and that's why we opted to use 12 kilometers per hour.
So in order to drive at the most optimal speed, the driver has to determine how fast the car is going. So a speed measurement system has been programmed onto the Arduino. This basically consists of an RPM sensor, a cogwheel with 2 magnets mounted on it, and 4 LED bars. These LED bars are all around the car, and the RPM sensor is inside the car, and the cogwheel is also inside the car, and the RPM sensor will measure when the magnets pass the sensor, and will then send an output to the Arduino. So first we had to create a program which would measure the speed of the car. So we started off with defining variables needed and the output of the RPM sensor, which would actually be 2-pin 50. So that will be the input on the Arduino. So those were defined first of all. Then to start off, in the setup we set all the variables which were needed to 0, and we created a syntax attach interrupt. This syntax would detach when the output of the RPM sensor was high, and then back to low. So that was when a magnet passes the sensor. So that's recognized on RPM sensor, which would be pin 50. It would then go to function speed, which would update, and then rising basically means when the input to the pin would be high to low. So that's what the sensor did. So then we had to create a loop in order to calculate the speed. So this is basically what we did. So the RPM is basically how many rotations per minute. So that will be 60,000 milliseconds over the time passed between one rotation. So actually, because there are two magnets inside and there's a ratio between two cogwheels, we had to time the 60,000 by 1/6, so that will be 10,000. So we could then calculate the RPM. The RPM, we could then transfer that to speed, as the circumference of one tire was roughly 39 centimeters. So so the RPM times the circumference of the tire would basically be the speed of the car, and then that's basically all it for the loop. So as the speed was then determined, we had to visualize the speed onto the LED bars. So there inside the motherboard there's an LED driver circuit which drives all the LEDs, and the LED bar basically consists of an array of 96 places, in which as the LED bar consists of 32 LEDs, each LED is basically has basically 3 colors, so red, green and blue, so RGB. So first all pins had to be defined, and as the driver consists of a clock, serial data in and a latch, these all had to be defined. So for each LED bar there were 3 pins which had to be defined. Then we could create a loop function, so in order to decide the color of the LEDs. So that's what you can see here. So it's now set between 4 and 2 meters per second. This can still be changed. So if the speed is larger than 4 meters per second, so then it will read the LED array, and it will set all pins to 2 plus 3, so 2, 5, 8, and so that will be all one color, and it will be the same for all the other colors. So it would turn blue if it's too slow, green if it's the right pace, and red if it's too fast. So then there's an update LED function which is called every loop, and it basically puts the clock and latch to high and low every time. So the LED bar keeps being updated, and the new data is always set to high. So there's always new data coming in, so the color can always change.
Now, the final subject we worked on for our project is the toll payment system. Now, the toll payment system is used to calculate lap times, and it's also a lap counter. Now, for the toll payment system, we have two separate systems, each containing 3 components. We have one system on the side of the track and one system in the car. Now, both systems contain a motherboard and a radio, but one radio is used to send and one radio is used to receive, and there's 2 parts of the IR system as well. So the 3 components of the side of the car are the IR receiver, which is an AX1838HS module, which is soldered onto this, which is attached to a ground. It's attached to pin 5 of the Arduino Duo motherboard in the car, and it's also attached to a power supply, which I also soldered some 47 microfarad capacitor and a 47 ohms resistance into it as well. So it all works how it should be. So there's a setup section and a loop section in the Arduino code for this system. Now, in the loop, basically what this says is the IR receiver is constantly looking for a new IR signal. Once it is received, it's here, if results value is 1, so the thing is received, the signal is received, it's going to write the car number of our group, which is 2, to a radio signal, and it's going to send it to the side of the track. So this is the code of the track. This is also a code of the track, and this is the code in the car. So what you can see here is every 25 milliseconds it's going to send an IR pulse containing a 1, which is defined in 2 digits. So every time it sends a 1. Now here, if the result is 1, so the signal is received, it's going to write the car number 2. So then it's going to resume receiving. But when the car number is sent, it's going to hear track radio read. Here it says radio write. So read, if the car number is read, it's going to calculate the interval in which it measures when the radio signal was sent. So by this interval, we can calculate the lap time. So to do this, go on. To do this, we all had to implement the speed measurement system and the toll payment system into one full Arduino code. Now, the full Arduino code contains a setup, which just contains the declarations, the definitions of all the different variables that we want to use in our code. Then it's going into a loop section, and the loop section is constantly calculating the RPM of the wheels. And every time the RPM is calculated, it's going to look if there's an IR signal received. If there's no IR signal received, it's going back into the loop to calculate the RPM of the wheels again. So every time a new RPM comes, it's going to go update the LEDs. So it's going to give us a new color onto the side of our car. Now, this is a constant thing. It's constantly updating the LEDs. But every time we can come past the finish line, it's going to receive that 1 that I talked about. So it's going to go send a 2 with the radio. Now, the thing is, speed measurement system, which needs to update the LEDs, and the radio sending system can work together. So we have a constant speed measurement system during the driving of our track. But once we get to the finish, it sends the number 2 to the side of the track, and the speed measurement system stops for a very brief moment. And that's how we implemented the full Arduino code with the speed measurement system and the toll payment system.
So at last, this is the logbook, so you can see how we work, what were our priorities. As you can see, the speed measurement code and toll payment code were our priorities, as we really want to do this right, as it would really show how we work. And as you can, the last part, the final design video, we worked on it a long time as well, and the last few days of our project we would work on the final report. Then this was our final design video, and thank you for listening.